To accompany the video about the meaning of the curl, a more geometric definition of the curl in 3 dimensions, let's talk about the meaning of the divergence. We're going to go to 3 dimensions in a second. Briefly, this is how I characterize it in 2 dimensions. It's a local flux density for any particular point where you want to calculate the divergence. You draw a little shape around it, circle, square, anything that you can systematically shrink to 0. And you look at the flux. Remember, this is our kind of funky way of denoting just the flux of this vector field. Because it's the flux through the boundary of a shape, unless we say very much otherwise, like put a minus sign here, it's going to be the outward flux, and that's always what we're going to use for this kind of definition. But then we divide it by the area, and it turns out when you do that, you get a very simple to calculate quantity. It's always finite, at least unless your vector field is really weird, and it turns out to be what people tell you is the definition of the divergence in 2 variables, 2 dimensions, which is just dp dx plus dq dy. And the way you can do that is you just do the midpoint method, and you look at the flux through this whole thing, just right at this point. You use this point to represent this whole side, and you just take the length of that side and dotted with the normal vector here and dotted with the vector field. Similarly here, dot the vector field with a normal vector here, dot whatever the vector field is with the normal vector here, dot the vector field here. It's pretty small here with the normal vector here. In a calculation that's very similar to something that our class does for the scalar curl, defined in a similar way as a local circulation density, you get something that's just derivatives, partial derivatives of the components. It's very pretty. So I'm going to take off on that into 3D. This is actually rather simpler than the story of the full 3D curl, the video that I just made of meaning of the curl. Again, it's no change in words at all. It's the local flux density. But now we've got a point in 3D space. We want to enclose that by something that talks about how much stuff is escaping some region. And so now this is the first place we're actually going to be looking at a 3D region, like a cube. We'll call it a cube. Well, you will use a cube. You could use a sphere or a ball bounded by a sphere. And so we're going to look at this cubical region. Again, let's say the side length is h. Let's call that ch, and then its boundary of ch is actually the 6 square faces. So the ch is going to be the actual 3D blob, and then boundary of that is the actual faces. So we can do the limit as h goes to 0, a 1 over, now it's going to be the volume, because density in 3 dimensions makes a lot more sense if it's volume density, of, and I'm going to write it out in words, and then I'm going to give you a little bit of integral notation, which is a little bit jumping the gun in terms of general fluxes, but we're going to totally be able to do this. The flux of f outward through the boundary of the cube. And then take the limit as h goes to 0. So it's a local, because of the limit, flux density. And then the only issue is, how do you calculate fluxes anyway? And it certainly helps if you've seen a little bit of those examples in physics, because we're going to do it in a way that's very similar to that. And then if you do that, there's some clever things you get. And does it come up with a formula like this? And of course, the punchline is if you've seen the usual partial derivative definition of the divergence, we know where this is going, and certainly would be analogous to this. So here's what we're going to do. We're going to do the same strategy. Oh, this is coming through here. We're going to take this 3 dimensions. We're going to take this cube. Let me draw a little bigger. Okay. And I'll tell you what, so it's centered at this point maybe. And I'll tell you what, we're just going to do the flux through the top face and the bottom face. Let's say the arrows happen to be kind of in similar directions, but they're kind of going in less here and they're going out more here, just to be definite. Okay. And I would like to get, if this is like a fluid, I would just like to get, if this is the rate of flow of the fluid at every point, I'd just like to get the total rate of flow through this square. Think of it as like a fishing net, some sort of thing that the water can go through, but maybe the fish will get caught. And you're talking about the rate at which fish are going to get caught. So here, because those vectors are smaller, they are going into the thing, but they're smaller. You're going to get a certain rate of stuff coming in and then a bigger rate coming out. Net, these two are going to contribute a positive outward flux to the total flux. And so we're going to do the same strategy as we did, as I alluded to in the 2D case, which is we're going to do an incredibly rough midpoint method. We're going to take the midpoint of this face. We're going to take the unit normal vector, which happens to be k, that's nice, outward, which is important. We're going to multiply it by the area of this guy, which is just going to be h squared. And we're going to pretend, basically, that the single vector right at the middle here, the single f vector right at the middle, that's not very Conevra, is representative of all the fluxes going through. And one of the things about flux is that if you're flowing parallel to the surface, you don't get any contribution. If you're going perfectly perpendicular, you get the full weight of the fluid flowing through. And so what we're going to get is f dot k times the area. So it's really just the component of f that's actually really is flowing across. That's all we need to know about flux for now. We're going to do more complicated stuff with integrals when it's not such a simplistic version, but I don't want to move that. But that's what it is going to be for now. So the flux out of the top is approximately, and this is the kind of approximately that's going to become an exact when we take the limit h goes to 0. So the area times just the vector field at, and you know what? Ooh, I'm going to cheat a little bit. Just to make this simple, I'm going to say, let's say we're analyzing it at 0. I forgot to do that. Okay. And it's just going to be the same it's going to be shifted if I moved it and analyzing it at any other point. But this is going to be at, let's see, had side length h. So this is going to be at 0, 0, h over 2. Dotted with k. So there's that component of the flow evaluated at the middle of the top, just the k component, outward k component, and then times the area, because we're assuming it's representative of all those arrows. Okay, and of course that's just h squared times r, if f is pi plus qj plus rk as usual, of 0, 0, h over 2. Okay, now the flux out of the bottom. To be consistent, we're going to look at what's the flux out of every single side. We're just going to do the top and bottom, and we'll see what the other ones are going to be by analogy. And so here we're going to take minus k as our normal vector, and we're going to dot the f vector. I've drawn them here going inside, but we're going to dot them with minus k. In this case, that would give negative, because flux in, the little bit of flow that's coming in here, we're going to count as negative flux out, usual kind of thing. And again, the area is h squared. So that's approximately h squared times f evaluated at 0, 0 minus h over 2 dot minus k. Very important. Almost forgot it. And that's minus h squared r of 0, 0 h over 2. Okay, so let's see. Remember, we were going to calculate in principle we want to do all 6, but I'm just going to show you the top and bottom contribution. We're going to divide by the volume, which is just h cubed, and take the limit. Okay, so the contribution to this notion of the divergence, just from top and bottom, that's going to be the limit as h goes to 0 of 1 over h cubed times h squared as a common factor, okay, times r of 0, 0 h over 2 minus r of 0, 0 minus h over 2. These cancel down to a 1 over h. Hey, guess what? This is just a symmetrized version. My class has seen this already. This is just a symmetrized version of the derivative of r, the partial derivative of r at 0, 0, 0 with respect to z. Just the definition of the derivative, just written in a little more symmetric form. And am I still on my screen? I'm still on my screen. And so that's equal to dr dz at 0, 0, 0. And if this had been like x naught, y naught, z0 plus h over 2. It would have been very similar. Okay, so the contribution to div f from the top and bottom is dr dz. Similarly, from the left and right, it's easy to verify that that is how much the j component changes as you go from the left to the right. In other words, as you change y. So that's dq dy. And what about from the front and the back? That has to do with how much this vector field changed. Remember that the key thing was that it was different on these two sides. If, well, little aside, if these vectors had been the same, then I would have gotten exactly the negative of f dot minus k here and f dot k here, and it would have all canceled out. That's because stuff is just flowing through or across. It's not actually net flowing out or in. Similarly, from the front and back, it's going to have to do with how the I component, which we usually call P, now I'm off my screen. The I component changes with X. So our total is that even if we start with this kind of funky, fluxy geometric definition of the the divergence, we do discover that yes, it has a wonderfully simple formula. And we always use this when we can as the formula. But when we get to the 3D divergence theorem, and also when we just look at pictures and want to get intuition about the divergence, this idea of put a little box around a point and ask, is it tending to flow out net or in, is really the better way to do it.